Welcome to the 9th lecture of graph theory. Today we will look at the concept of connectivity in graphs. There are two kinds of connectivity. We are going to discuss both of them. First, it is about vertex connectivity, the second edge connectivity. So, intuitively connectivity is something about whether the given graph, how well the given graph is connected. So, we need to understand what it means. Say the most natural way to define it probably is this. Consider two vertices x and y, and then we can say two paths from x to y, I call it xy paths p and q in G are internally disjoint if they share only the n vertices. For instance, if these are the two vertices x and y, and suppose this is one path p between x and y, this is p, and here is another path q between the same two vertices x and y. We say that these two xy paths, these are xy paths, internally vertex disjoint if they share only the beginning and end vertices. That means this and this, so this will not be in this path, and this any of the vertices here will not be in this path. So, the local connectivity between x and y, so we can call it p of x comma y, is defined as the maximum possible number of internally vertex disjoint paths between x and y. For instance, here in this graph, suppose I have some more paths, right. Suppose I put several connections here, maybe even some connection like this. So, how many internally vertex disjoint paths can we see? So, it is possible that there are several paths, but then if you are looking about internally vertex disjoint paths, I can take this one, then I can take say this one, and I can take this one. I can take this edge itself, it is internally vertex disjoint with other paths I have already selected, and this one, and this is all internally vertex disjoint. I got 1, 2, 3, 4, 5. I cannot take more than this because see. So, this is the local connectivity between x and y. The graph can be much complicated. There can be other vertices, but it may so happens that if you cut all these paths, right. So, then if you take all these paths, then any other path has to share some vertices with one of these paths. That is what it means. So, they will not be, if you take one more path, then the entire collection together will not be internally vertex disjoint. So, now what is the connectivity of a graph? You have several pairs of vertices x, y in the graph, and then for every pair you have a so called local connectivity, right. The local connectivity between x and y is the maximum number of internally pairwise internally disjoint xy paths, right. So, among all the pairs you look for the minimum local connectivity, that is going to be the connectivity of the graph. This makes sense. So, you can take some examples. For instance, let us look at this graph. Simple. Here I can take, this is 1, 2, 3, 4. Between 1 and 3 or 1 and 2, there is only one internally vertex disjoint path. There is nothing more you can take between like that 2 and so this is 5, 2 and 5, 3 and 5, 4 and 5, everything is 1, and between 1 and 3 you get only one internally vertex disjoint path, namely this one, right. So, any pair if you consider, there is only one internally vertex disjoint path, and therefore, the minimum over all pairs, if the local connectivity of that x y pair, if you minimize over all pairs x y, then you will get only one here for this graph. So, here the connectivity of this graph is going to be 1. So, now let us take a little more complicated example, than the earlier one. So, this is okay, it's still simple, but here you can see that if I want between x and y, what is the local connectivity? There is one path here, there is another path I can take. Any other path I try to take, for instance, if I try to use this thing, I will have to go via this, and then I have already used this one, right. So, then they will not be internally vertex disjoint. So, I cannot add anything more. These are the only two things. Now, so like that, so between this pair also I have two internally vertex disjoint paths. So, but on the other hand, if I take this x and this z, then I have this path, I can get one. Any other one, because that one has to go through this middle one, any other one will have to go through the same vertex. So, it will share an internal vertex. So, it will not be internally vertex disjoint. So, with this P and Z, the local connectivity of Pz is going to be 1. So, when you minimize over all pairs, then the local connectivity has to be less than equal to 1, but then we know that it cannot be 0, because between any two pair there is at least one vertex. So, we use kappa to denote the connectivity of the graph. This is not this one, this is P with local connectivity, kappa is the connectivity of the graph when you minimize over all pairs. So, this is the most natural notion of this thing. Now, you should understand that when I consider two vertices x and x, same vertex, then you cannot define this thing. So, we do not worry about x and y being same. So, consider a complete graph Kn. Now, what will be the connectivity of Kn by our definition here? So, you can take any two vertices x and y here. You know there is one path between them, and also you have total n minus 2 other edges going out of it. These edges reaches several different vertices. You can, from any of them I can come back to here like this, isn't it? So, therefore, the total is 1 here, and this n minus 2, total n minus 1. So, this is the thing. So, if you have a trivial vertex, just one vertex, you can take it as one connected. So, connectivity as 1. So, it is by convention, in fact there is because anyway here our definition that minimize over all pairs does not make sense, because there is only one vertex here, right. So, now there is one intuitive definition of the definition of connectivity, which is like what we will think when we hear the word connectivity. It is trying to capture our intuitive notion of what connectivity should mean. Now, but here is a slightly non-intuitive way of doing it. Here it says let x and y be distinct non-adjacent vertices of G. So, here in the graph I pick up two vertices with the condition that they are non-adjacent, there is no edge between them. Now, you try to disconnect x from y in the graph by removing some vertices other than x and y. Outside x and y, we remove some vertices and try to make sure that in the remaining graph there is no path from x to y anymore. So, then ask what is the minimum number of vertices you have to remove to do that. Such a collection of vertices by removing which you can make sure that in the remaining graph we have x in one of the components of g minus xy, and y in another component, right. Here xy vertex cut, it is called such a vertex, such a subset of v minus xy. So, we are not allowed to take x and y in the subset S. Such a subset xy S is called an xy vertex cut. So, an xy vertex cut is a subset S of v minus xy such that x and y belong to different components of G minus S. So, we can look at some examples. For instance, here let us take our graph which we drew earlier. Here you suppose if you want to, they take two non-adjacent pair, that means you should not take, suppose if I pick up x, I should take say z here. Now, to disconnect x from y, what you can do is remove this set S, right. Then in the resulting graph, so nothing will be there. So, we will, the resulting graph after removing S will look like this x, y and then z, say z dash. So, x is in one of the component and z is in a different component. You have no path starting from x and reaching z in the resulting component. So, this is such a vertex xy vertex cut. Now, I can consider another example here. So, let us see, consider this graph where right in this graph, if I want to disconnect say x from z, so sorry, this is an x and say I take it as xy, and so then definitely I have to disconnect this vertex. So, I will mark it with green, this vertex is to be disconnected, and then this is to be disconnected, this is to be disconnected. So, these three vertices are to be disconnected if I want to disconnect x from y. So, therefore, this is an xy vertex cut here and its cardinality is 3. Okay. So, this xy vertex cut, the cardinality of the minimum xy vertex cut and over all possible xy will give you the minimum number of vertices that we have to remove so that the graph gets disconnected, right. So, for instance, when if the graph gets disconnected, in the remaining graph there should be at least one pair such that x is on one side and the y is on the other side, and naturally those two vertices are non-adjacent in the original graph. Now, to find out the minimum number of vertices that we have to remove from the graph, so that the graph after removal of this vertex is a disconnected graph, what we can do is over all pairs x comma y which are non-adjacent, we can find the cardinality of the minimum xy cut, and this minimum will be the minimum number of vertices required to disconnect the graph. So, this is another way of, this number is another way of defining connectivity, because finally we are talking about removing the minimum number of vertices so that the graph gets disconnected. So, but these two notions look a little different at the first look, but it so happens that they are the same. We will later study a theorem called Mensgers Theorem, which states that both these notions are equivalent. Now, just before moving further, I will mention that there is something called edge connectivity also. Here we were naturally there, it is very parallel. So, we can we can define edge connectivity in two different ways, like we did for vertex connectivity. One is by considering any two vertices x and y, and consider the number of pairwise edge disjoint xy paths. Now, there is nothing like internally edge disjoint here, because you are given two vertices, the edge set they should be totally disjoint. In fact, the edge set of the two different paths xy paths should be disjoint. That is, like that we have to get the maximum number of pairwise edge disjoint xy paths, and this number is the local edge connectivity, and this is denoted like p dash xy. Remember, p of xy denoted the local xy vertex connectivity, but p dash xy will correspondingly denote the edge connectivity between x and y. So, we will say that a non-trivial graph G is k edge connected if for every pair UV the local connectivity is greater than or equal to k, which means that you have at least k edge disjoint paths between any two pair of vertices. The edge connectivity k dash of G. So, k of G was used for kappa of G, the kappa of G was used for vertex connectivity. Now, edge connectivity is defined denoted by k dash of G, kappa dash of G, and kappa dash of G of a graph G is the maximum value of the value of k for which G is k edge connected. So, or in other words, you can in the graph you can consider all pairs x y, you can consider the minimum local edge connectivity, and that is over all the pairs, and that is going to be this value, right. So, like just like in the edge vertex version. Similarly, so we can have a different notion like how many edges are to be removed from the graph, so that the graph gets disconnected. This is another notion to define the edge connectivity, and then we will show that both these notions are equivalent. So, we will come back to these notions later again. So, yeah, we will come back to this notion later. Now, we can quickly see one interesting observation. The vertex connectivity is always less than equal to edge connectivity, and that is going to be less than equal to minimum degree, because you see the vertex, if you remove if k dash happens to be the minimum number of edges that is to be removed, so that the graph gets disconnected, you can remove one endpoint from each edge. All those edges will anyway gets removed, right. So, therefore, the vertex connectivity is going to be at most the edge connectivity. What you do is you consider a collection of edges by removing which the graph gets disconnected. Now, you can remove one endpoint of each edge, that means one vertex for one edge. So, naturally the graph gets disconnected with this thing, this if you remove these vertices, because all the edges in the edge cut, that is what it is called, like vertex cut we have edge cut. So, this will disconnect the graph. So, naturally that gave us a vertex cut also, and because the kappa being the minimum cardinality of a vertex cut. So, we can infer that kappa is less than equal to kappa dash, and that is less than equal to minimum degree. Why? Because the minimum, if minimum degree is the smallest degree of a graph, the number of neighbors of a vertex, smallest number of neighbors of a vertex over all vertices. Of course, because we are talking about simple graphs. So, they are also equal to the number of edges that is to be removed. So, that is connecting the vertex to the rest of the graph. So, if you remove these edges, definitely that vertex get separated from the remaining part of the graph. So, naturally that is an edge cut, and therefore, the actual minimum edge cut is going to be even less than equal to that, it can even be less than that. So, kappa dash is less than equal to delta. So, this is one quick observation that we can make about the edge connectivity, vertex connectivity, edge connectivity, and minimum degree of a graph. Now, let us before going further and looking at statements like Mensgers Theorem, where we say that the two equivalent, two notions of connectivity that discussed, both for the vertex version and the edge version. Two different type of connectivity discussed. One was based on number of paths between vertices, the other was based on the number of vertices to remove from the graph, so that the graph gets disconnected. So, later we want to prove one theorem called Mensgers Theorem, which states that both these notions are equivalent. But before that, we will just look at the two connected graphs. How will they look like? This is our aim. So, here is one definition. So, you know that in a graph, a maximal connected subgraph is going to be a component, right. So, like that you can take in a two connected graph, you can look for a connected graph, you can in a connected graph you can look for a maximal connected subgraph without a cut vertex is called a block. What is a cut vertex? So, in our examples, so here you remember we have this is a cut vertex, this is one vertex by removing which the graph gets disconnected, right. So, suppose you are looking for in this, you are looking for a maximal, so here suppose I add this also here. So, you look at this one, this is with without a cut vertex, because by removing this thing the graph does not get disconnected, or removing this thing the graph does not get disconnected. For instance, this alone if I consider. Now, so I can add something more. So, I can take this thing, this is a this is a maximal component, maximal connected subgraph without a cut vertex, right, because there is no cut vertex in this triangle. But now, if I take a little more, for instance, if I take this much, then naturally this will be a cut vertex. So, we cannot add any more vertices there, because this cut vertex comes. So, so here in this graph the maximal connected subgraphs without a cut vertex happens to be in this graph, right. I mark it like with this one, and then of course this one, and this one, right. This is also one, for instance, this is edge. If you remove one vertex, so this is still connected, right, that is max. So, that is that, therefore, they are not cut vertices. So, this is the way we can decompose a given connected graph into several maximal connected subgraph without cut vertex. So, it may look like a little. So, typically the structure may be, structure of a connected graph can be like this. So, it can be like this. Sometimes you can get some edges, you can get some edges, right. So, it can be something like this. So, these are all maximal, see, these are all maximal things. These edges I mark because they are important. So, here look in this thing, this is a two connected subgraph, this connectivity of this thing is 2, and this is also 2 connected. There is no, because within that there is no cut vertices, within that there is no cut vertex. So, these things are the blocks, and see one, this will be the picture we will get. For instance, if you look at the graph abstractly a little, as if you are looking from a distance, this is the look. So, now you can see some kind of tree structure here among the blocks, while this you consider as some super node, and then the edges here is represented by the cut vertex on which these two blocks are pasted. So, this idea is expressed in the next statement, which says that the block graph of a connected graph is a tree. What do I mean by a block graph? In a block graph, block graph is a bipartite graph. What do? Each of the blocks will be taken as a vertex. This is say B1, the block 1, this is block 2, this is block 3, this is block 4, this is block 5, this is block 6, this is block 7, this is block 8, this is block 9. and each of the blocks, so the blocks will become vertices, and yeah, this is so the blocks. So then I can make a bipartite graph like this by putting B1, B2 up to B9 here, the blocks, and then on this side I can collect the cut vertices of the graph and put. So which are the cut vertices of this graph? Here 1, C1, this is C2, this is C3, here this one, and here this is C4, this is C5, and this is C6, like that. The cut vertices can be taken, and then I will this is C1, C2, C3, C4, C6, these are the, and then now if B1 contains C1, then you put this edge. So go here, see, you know, C1 is contained in B1 and B2, so therefore both B1 and B2 will be connected to this. Similarly, let us look at this one, this is C6, C6 is contained in B7, B8 and B9. So B7, B8 and B9, all of them will be connected to C6, this being the C6, right. So this graph is called the block graph. The blocks and cut vertices, blocks on one side of the bipartite graph, cut vertex on the other graph, and then the cut vertex, if a cut vertex Ci is inside a block Bj, then Bi Bj is connected. So we say that this is a tree. It's rather easy to prove. See, you can more or less see it from this picture. For instance, if I had this cut vertices becomes the edges, and this becomes the nodes, right. Therefore, you can see the tree structure here. So tree structure here somehow. So intuitively, it's very obvious, but we will not prove it. But I will leave it to the students to prove it. Now this is the structure of two connected graphs. Now what about two connected graphs? For instance, there are no cut vertices in it, and also it's two connected in the sense that to disconnect the graph, we need to remove at least two vertices from the graph. By removing one vertex, you cannot disconnect. For instance, this graph is not two connected because this vertex, if you remove, then the graph gets disconnected, while this graph is two connected because you remove any one vertex from this thing, it will not get disconnected, a path remains here, right. So therefore, it is two connected graph. This is two connected, but this one is not two connected. So see, these graphs have an interesting way to construct a there is an interesting way to construct a two connected graph. What do you do? So we can essentially construct by give me any two connected graph G. What we can do is we can start from a cycle in it and then keep adding something called years. What do you call year? So you start something from this already existing graph. So and then initially it will be a cycle. So this is an year. That means it can be just an edge starting at a vertex of this thing and reaching another vertex, or it can be something like this, a path such that only the last two vertices are on this thing and the rest is just a simple path. Now this is a new graph, and on top of this thing you can add an ear like this, say maybe like this, or it can be like this, right. So this new graph can be added. So then so you can we see that if I start with a cycle and keep adding years, sometimes the years to an already existing graph H, this is an already existing graph, and an ear is also called an edge path, in the sense that it is a path outside edge with just the n vertices placed in edge, the n vertices placed in edge. This is one possibility, right, then vertices placed in edge. So, this is called an edge path. So, we will say keep saying ears rather than saying edge path. Edge path is also a word which is commonly used. Now, suppose I start with a cycle and then keep adding ears, as I mentioned earlier, then is it possible that all the time I will end up with a two connect graph, or is it possible that I may lose my two connectivity in some point? It is very easy to verify that it will never happen, because so if I am adding an ear of this sort, then it is because you are just adding an extra edge, it is not going to trouble you. But if you are adding an ear of this sort, right, adding an ear of this sort, then also you know that within this any two vertices have so this cannot be disconnected so into two components by removing less than two vertices, that only one vertex removal of one vertex will never disconnect this graph. But then suppose it is getting disconnected by removing one vertex, it should be that some of these vertex, this or this, that should go out. But then which vertex should disconnect it? Because see, this is a path, any vertex if it is going into one connected component. So, you have two different ways to enter this already existing graph H, right. So, therefore, it is not possible to remove just one vertex and disconnect any of them from here. So, therefore, by adding an ear you are not going to lose two connectivity. So, by when we add ears, to a two connected graph, we again get a two connected graph. This is very obvious, but what can probably happen is that what can probably happen is see, so there can be some graph G. So, this is what we are bothered about. Suppose some arbitrary graph G, two connected graph, but see, by starting from a cycle and adding ears to it like that, adding ears one after the other, what is the guarantee that we can make this thing this way? So, we will prove this thing. So, first we will identify a cycle in it, because it should have a cycle. So, because it is two connected. So, for instance, any two vertices if you take, there will be a two vertex internally vertex disjoint paths, and there should be a cycle in it. So, we start with a cycle, right, and now the cycle to the cycle we will add ears. For instance, see this graph G we will look at, maybe this cycle comes here like this. So, now from the ear means I cannot arbitrarily add an ear, the ear should be existing in this thing. So, in this graph if I try to locate an ear and then add it to that, and then already existing graph I will add already constructed graph I will add another ear, from as long as this path is available in G I will add it as an ear. And then so sometimes the ears can be like this, some simple edges, I will keep adding. As long as I can add an ear, I will add it, and at some point I will have to stop. So, there are two reasons to stop. Either G all the vertices and edges in G are already added here. So, that means I have already constructed G starting with my original cycle and then by adding ears. So, that is a good situation. That means I have shown that G can be constructed by this procedure, starting with a simple cycle in G and by adding years one after the other we can construct G. Another way is that so you may just stop and then something may remain outside, right. So, some vertices and possibly some edges among them, whatever, some graph, some vertices, and then is it possible that something like this remains. So, this is not, but no, that nothing like that, because if such a thing is not yet added, you can always add, because it is an year, right, by itself you can add. We are saying that if you can add a new year, you will add it. So, that means what we have already constructed is an induced subgraph of G, if not G. So, that means there are some vertices outside. So, let us say here is a vertex outside G, and here is a vertex outside G, and this G is definitely, because of the two connected, there should be a path from here to here, right. There should be a path from here, and then of course it is it's an, see, it is not that all the paths which start from here goes this thing. So, there should be one more path starting from here, and because otherwise if I remove this vertex it will get disconnected. So, there should be two paths starting from here to here. So, this vertex to this thing, and there can be some other vertices here of course, but then there should be two different paths, because otherwise what will happen is, so more rigorously what I can say is, I will consider a vertex outside, because it is connected, there should be something which is directly adjacent, right, and then from this thing, if I have only this connection, definitely by removing this vertex I will disconnect it. So, there should be one more path. At that one more path will come, take some vertices outside, and first look at the first vertex it touches, the internal inner vertex which touches, right, the vertex of this already constructed graph. So, if it is this itself, then again it is a cut vertex, right. So, that means if I remove this vertex, all these things will get removed. So, it should come and touch another place, it should come and touch another place. So, that is going to be an year, right, we can take it as an year and add. So, our assumption that the graph where we stopped, induced subgraph with which we stopped, was one where we could not make any progress, that is a wrong assumption, that is a wrong assumption. So, that is what it says, in other words. So, if you want to understand the year decomposition of a Peterson graph, this is a Peterson graph like this, right. So, look at this graph, simple graph is a Peterson graph. If this Peterson graph, if you want to look at an year decomposition, now I can start with a cycle, this cycle, it is a simple cycle, and then you can add this year, right, you can add this year, and then you can add this year, right, then you can add, say, the new year, you can add this new year, right, and then the remaining years are this edge, right. So, you got this Peterson graph constructed. This is the year decomposition. Our proof told that any two connected graph can be constructed starting from a simple cycle in this way. In this way means by adding years one after the other. We will not get stuck. If we get stuck, there will be one vertex outside, and that vertex, there will be one vertex which is adjacent to the already constructed graph outside, and from then that vertex there should be one more path coming back to the already constructed graph because of the 2 connectivity, and this entry vertex, the other entry vertex cannot be the same vertex again because of the 2 connectivity, and that will provide you an ear. That is the idea. Now, what about 3 connectivity? So, in the 3 connectivity, so also in 3 connected graphs also, do we have some such theorem that starting from a simple graph we can construct any 3 connected graphs. So, this theorem called Tutt's theorem, it says a graph is 3 connected if and only if there exists a sequence G0, G1, Gn of graphs such that the following properties hold. G0 is equal to K4 and Gn equal to G, and Gi plus 1 has an edge xy with both the degrees of x and y greater than or equal to 3, and from Gi plus 1 we can see, we can get Gi by contracting the edge xy, right. So, this such a sequence exists, or in other words, suppose you are given the graph G. So, we say that it is 3 connected, it is 3 connected. That means to disconnect this graph you need to remove at least 3 vertices, at least 3 vertices are to be removed, otherwise it will not disconnect at all. Now, in such a graph what we can do is we can find some edge such that it can be contracted, and then you will get a smaller graph which is again 3 connected. This is Gn, this is Gn minus 1. By contracting the vertex, number of vertices is removed by 1. The point is we will be able to pick up a vertex in this edge in this thing xy such that by contracting xy we will end up a smaller graph Gn minus 1 such that this is also 3 connected, and here again you will be able to find another vertex, say x1 y1, such that when you contract this thing we will end up with a graph, smaller graph Gn minus 2, right, which is obtained by Gn minus 1 bar x1 y1, right. So, this is, so this graph will also be 3 connected, and you can 3 connected, you can keep on doing it, and finally because every time you are reducing the vertices by 1 you end up with the beginning graph, right, G, which is essentially K4 equal to K4, because why, to begin with we have if there is 3 vertices only, then definitely it is not 3 connected, right, it is only 2 connected. So, maximum, because the triangle is only 2 connected. So, it should have at least 4 vertices, and it has to be when it reaches the stage that it is only 4 vertices, and because it is 3 connected it has to be K4, because the smaller graphs are not 3 connected. So, if you remove one edge from K4 it is not 3 connected. So, in K4 you have to stop this thing. So, this is possible is what you are saying. The theorem says that any graph G which is 3 connected can be reduced to K4 in this way. By contracting an edge here you will get a smaller graph, contracting an edge here you will get a smaller graph, like that you can reach K4. So, in other words, starting from K4 any 3 connected graph can be reached in a sequence like this, right. This is essentially what it says. Now, the key lemma we need to prove this thing is given here, and it says if G is a 3 connected graph and the number of vertices in it is more than 4, then G has an edge E such that G, the graph obtained by contracting E, G bar E, is again G. See, after this is the graph obtained from G by contracting the edge E, is again 3 connected. Remember what is this contracting? So, this contracting essentially means, so if x and xy is an edge, and these are the neighbors of x, and these are the neighbors of y. Maybe some sharing is also there. So then you contract, so you make this one vertex, and all the neighbors of x and y together will become the neighbors of this thing. If they were common neighbors, then a multiple edge will come, that we will discard. So essentially all the neighbors of x and y together will become the neighbor of the new vertex vxy. This is the contracted vertex, the vertex obtained after contraction. So this so now we are going to say that, so as you can easily understand, to prove the previous statement at least one side, that means given a 3 connected graph you can reach K4 by contracting edge of, so one edge here and then another edge here, another edge here. You just have to show that in any 3 connected graph there is an edge that can be contracted, so that the 3 connectivity is retained. Because this is a 3 connected graph, you will get such an edge if such a statement is true. And then this is again 3 connected graph, because such an we contracted an edge which will allow us to retain the 3 connectivity. And this is again a 3 connected graph, there is another edge in it which when contracted will allow us to retain the 3 connectivity. So we can contract it, and what we get after that is again a 3 connected graph. So this reduction should happen, reduction in the number of vertices without losing the 3 connectedness. So finally when we reach K4, so it has so 4 vertices, it has to be K4, that is all, right. So therefore we only have to prove this, that is in a 3 connected graph, in any 3 connected graph there is at least one vertex which can be contracted without losing the property of 3 connectivity. How am I going to prove this thing? So here, so this is the thing. So you take this 3 connected graph G, and then you can consider this edge xy. Suppose there is an edge xy here. So this edge xy is, if I suppose there is no edge xy with the desired property, that means any edge xy if I take, if I contract it, then what happens is, so with this new, this replaced by vxy, the resulting graph G1 that I get from G is such that it is such that its 3 connectivity is lost. That means it gets a 2 separator, that means a vertex cut of cardinality 2. So what does it mean? Suppose that means any edge, if I, any edge xy, if I will get some separator somewhere, some vertex separator with 2 vertices, just 2 vertices in it. This will be on one side, this will be on the, when I after contracting this. But is it possible that this contracted vertex is completely here, that, sorry, not completely here, that here, but is not in the separator, it is here? Of course not, because in that case if I had done the reverse operation and then put back the edge xy, then what will happen is this 2 length separator would have separated the original graph G itself, right. In the G also this would work as a separator then, you understand it, because x and y when after contracting it, so if it so happens that there is this 2 separator, then y before contracting, because that's anyway here on one side, this separator would have separated that from the remaining part in any way. So therefore neither can we have both x and y here, that means vxy here or vxy here. So then where can vxy be? So it can only be here, vxy can be inside the separator only, vxy can be only inside the separator. So we can, for any edge xy, when we contract, the graph obtained will be such that it will have a separator, and that's a 2 separator, and one of these vertices in the separator will be vxy, and there will be another one. Let's say this vertex is called z. So vxy comma z is our separator. So if I put this x and y back here, so in the original graph we see x, y and z. These 3 vertices together is a separator for the original graph, because if this separates, this, when this and this together can remove only those edges which this removes here, right. So, because they are all adjacent to either this or this. So, if I remove x and y both, then the separation will happen even in the original graph. So, if Vxy z is a separator for this graph after contraction, then x comma y comma z is a separator, 3 separator for the graph before the original graph G, the first graph itself. Now, I will say that given any edge xy, I have one set such that xy comma z is a separator of the graph. So, give me an edge xy, then I can find a set for it such that these 3 together is a minimum separator, not just separator, minimum separator. Why? Because it is a 3 connected graph, minimum vertex cut. Minimum separator means minimum vertex cut, minimum separator of G. Okay, is a minimum separator of G. Now, let me try to, this is for an edge, Z is the partner of it in some sense, and let us say x for each 3 tuple of this sort, let me assign a value. How do I compute the value? Now, I consider this separator x, y, z in the graph G, and I will, there will be several components, right. So, for instance, there will be this component C also, which happens to be the smallest component in G minus x, y, z. If I remove x, y, z, the graph gets disconnected, and among the components which results, I will look for the smallest component. The cardinality, the number of vertices in the smallest component will be the value of this one. I will say this is the value of this set, this xy set. So, like that for each edge and its partner set, not that there is a unique set that I can get. So, you can consider the one which will partner one which will give you get you the minimum value if you want so. So, that way for every edge xy a partner is available, and with respect to this xy and its partner z, together we can evaluate its value by removing these 3 vertices in the graph and looking at the components and finding out the minimum cardinality component, and the cardinality of the minimum component will be the value of that. Now, among all possible edges xy in the graph, I will look for the one which will achieve the minimum value. Not that it is unique, it may be possible that there are more than one edges, but I will pick up one such edge. Now, from now on when I say xy, that is an edge, and together with its partner, so the value of it is going to be the minimum. That means, when I remove x, y and z from the graph, there exists a component C, and then the cardinality of that component is such that if you remove any other 2 edges, any other edge x dash, y dash and its partner z dash, any component which is produced will be greater than or equal to this in cardinality, in the size, in number of vertices. So, such an xy, once you get such an xy, so I will show a contradiction. So, here we have xy, and you can look at the minimum component C of it, sorry, this is xy set. So, it should say xy set. Now, one property of a minimum separator is very important, that is if it is a minimum separator, for this xy z is a minimum separator, it should have an edge, this x should have an edge to each of the component, and z should have an edge to each of the component, y should have an edge to each of the component. Why is it so? Suppose not. For instance, if there is this A, B, C is a minimum separator, and there is a component here to which only A and B are connected, C is not connected. So, there are other components also, right? That is why it is a minimal separator. Then naturally, if I remove A and B alone, I can cut away this portion from the rest, right. So, there will be a 2 separator, and the assumption that the graph is 3 connected will be wrong. So, therefore, in any minimum separator, we will have the property that every vertex in the minimum separator is connected to every component by an edge, like I showed you here, right. Now, this property allows us to infer that. So, going back here allows us to infer that when I consider this my xy set, when I consider my xy set and my smallest component C, there are other components. This is the smallest component, and this happens to be the smallest among all possible xy sets, right, which I select. So, there will be one vertex V here to which it is adjacent, because there should be an edge going here, and that end of this edge be called V. Now, ZV is an edge, and there is another vertex W somewhere, I do not know where, somewhere, such that Z V W, these three set is a separator of the graph, given graph. Now, you can consider this Z V W, this is a separator of the given graph. Now, I want to see what will happen to my component C. Of course, the component C cannot become smaller at all. If it becomes smaller, then it is a contradiction, because see, C means it may not be as such. The vertices of C, you have already pulled V away from this thing. So, it is already becoming smaller, right, it is getting smaller. So, if it gets disconnected here because I pulled away V, then we got even smaller component, but that is not allowed, because you removed V, something more should add to that, and then you should get a component at least as big as the original C. But then the C is connected. So, if you go back to the earlier picture, the C is connected only to x and y other than this C component. The component C is connected to only to x and y other than see, it is not possible to connect only to x, not connect to y, because once you get x, y will automatically come, because this is an edge, right. So, that means it should capture x and y, and later once you capture x and y, you can capture more things. So, it is possible that x and y should, it is important that x and y should be part of the component which contains C. You removed V, but then x and y should balance it. But the difficulty is, if that happened, where will all the neighbors of V go? So, remember V was a vertex in C, and then we can now we will discuss it in the next class. So, we will complete the proof in the next class. We will need some time. Thank you.